Good morning. Welcome to Krishna's class. Let us continue with the exploration of the Lebesgue integration theory. In fact, the next step in the stage of development of it. Last time we considered bounded measurable functions, bounded measurable on a set of finite measures. And in fact, we proved that all bounded measurable functions on a set of finite measure are integrable. This is what we okay. So we proved the integrability of such functions. We observed that for an interval AB, contained in R, the class of all Riemann integral functions are Lebesgue integral. In fact, you see that this comes under the above consideration because all Riemann integrable functions on the interval AB are have the property that have when we have considered only bounded real valued functions on the interval AB, which is a bounded interval. And then we explore the Riemann integrability of such functions. We found that we had to throw out a few functions so that only the rest of them is Riemann integral. So the class that we have considered for Lebesgue integration is larger than the class of Riemann integrable. So let me designate it by, so we observe the following. So we have R AB is properly contained in the Lebesgue integrable functions on the interval AB. Okay. Now this containment is proper. Okay. So we have seen that the Dirichlet function is not Riemann integral. It's probably worthwhile to have a look at this function. So the Dirichlet function is the characteristic function of the interval 0, 1 intersection the set of all rational. That means the function which is equal to 1 at Q and 0 complement. This is the definition. Then we have investigated this function, like the Riemann integral of the reason is the following. No matter what partition we introduce, on 0, 1, every interval contains both rational and irrational. This implies, see, that the upper integral the lower integral of f is equal to 0, which is not equal to 1, which is the upper integral of, just look into Riemann integration. Okay, and the consequence is that it's not Riemann over the interval 0. On the other hand, if the Lebesgue integrable functions on the interval 0. Now this is quite easy to see, because you see that fx equal to uh, 1 times the characteristic function of Q plus 0 times the characteristic function of two complement. And therefore, from what we have already seen, integral of f on 0, 1, that is the Lebesgue integral of this is equal to 1 times measure of zero times measure of now this is equal to 1 times 0 because we are only considering only the rational points, which is a countable subset of 0, 1, and therefore its Lebesgue measure is equal to 0. The Lebesgue measure of all countable sets are have Lebesgue measure 0 plus 1 0 times the measure of 0 1 intersection q complement. That means the set of all irrational points on the interval 0 1, and you see that the measure of the interval 0 1 is 1 and the measure of rational points is 0. Therefore, the measure of irrational points, which is the complement of that, is equal to 1. So you see, compare these two. Okay. So the Lebesgue integral exists. So in fact, this is only one function, but there are several functions on the interval 0 1 which are not Riemann integrable but Lebesgue integrable. But all Lebesgue integrable functions on the interval 0 1 are Riemann integrable. Okay, and not only that, the two integrals coincide. Okay. Moreover, what we have is that for all Riemann integrations are Lebesgue integrable and the two integrals coincide. Are Lebesgue integrable. And the integrals therefore, the Lebesgue integration that we have pursued is a natural generalization of the humanity. Now, this is the important thing that we have hit upon a very natural way of generalizing the Riemann integral, and it has gains also. In fact, we could get more functions into this class. In fact, we could go far, far beyond, as we shall see when we take up the next steps of processing integration or advancing the integration theory. Okay, so that is one observation. Now we look at some of the properties. The Lebesgue integral linear operation. That is the first property. That is integral of the Lebesgue integral of that means if f and g are Lebesgue integrable, then alpha f plus beta g is Lebesgue integrable, and the Lebesgue integral and the Lebesgue integral of is equal to whatever domain we have, alpha times beta times Lebesgue integral of g. Well, the monotonicity property is satisfied. Monotone. In the sense that if f the bounded measurable set is, and then we have third property is that it is additive that is let of P with A intersection B M. I mean, right now we are only talking about bounded measurable sets, integrable over E, and of course, then now this is what you mean by over disjoint sets, it is additive. Okay, so these are some of the properties. Now we'll take up the convergence problem. Suppose Fn is a sequence of bounded measurable functions defined with finite measure. We call this uniform suppose F uniformly converges. This is not just merely pointwise convergence, but uniform convergence as defined in the usual way. Then, of course, the limiting function bounded, measurable, bounded, measurable on E, and the integral also. When I write this, I am talking about the Lebesgue integral. I don't want to write that L all along. Converges to it is limit intending to of integral of Fn over E or in short you can see that what this says is that the integral and the limiting process commute. Okay, so this is happening under some conditions. The conditions are, of course, on the convergence, we demand uniform convergence. So, to give some insight into this, the strength of this condition, we show that if this is not true, then we cannot assure the outcome of this theorem. In the absence of uniform cut, that is near pointwise convergence, not enough. To assure the content of the above theorem. Give some example. Define Fn. Zero in Fn x equal to 0 for x greater than and Fn is linear or etc. So if you look at the graph of this function, something like this. Suppose we define. So suppose we take this as 1 by this is 2 by n. Then the function is something like this. This is the graph of the function. It's linear on this part and it is linear on this part. And then this is the graph of the function. If you want, you can highlight it in a color. And you have this is equal to That is your Fn. That's the graph of it. Okay. Now you see that goes to 0 as n tends to for every x. Now you look at the integral. So you can easily calculate this usual integral, the Lebesgue integral for every integral of because f is identically 0. Therefore, what do you get? This is equal to 1 not equal to 0 okay. So the conditions of that theorem are violated. Okay. Note that the convergence that you can easily check. This is 0 and you can easily see that it's not uniform. It's not just uniform convergence, but there are other conditions which guarantee this interchange of limit and summation. So you take the bounded convergence. Here you can see that the sequence is not bounded. Okay? Sequence is not bounded. Not a bounded sequence. Okay. So let E be a measurable set, the big measurable set, and measure of finite. And that is the Lebesgue measure of E finite. Then Fn assume is uniformly bounded. It's not uniformly bounded. That is, there exists M positive such that for every year. If pointwise on E, then what you can assert is that the limiting process and the integration can be interchanged. That means commuting. This is the bounded convergence. Okay. This uniformly bounded, this is what. So that completes our, and you see that the example that we have looked at earlier does not meet these conditions. Okay. That's obvious. Does not meet the conditions stated in this theorem because it is not, the Fn is not uniformly bounded by some. Okay. So that is clear. Right. Now that's a stage from where we can go to the next level. So further level of this integration thing. So we take up now Lebesgue integral of a measurable non-negative function on a set E a support of so this is the next thing that we want to take. Okay, so this is the step 2, what I call the step. So let us look at the conditions here where we have relaxed and where we have not. There are a lot of things to be explained here. One, of course, we are talking about a measurable non-negative function on a set E with a support of finite measure. Okay, lot of things are to be explained. First of all, we observe that we are no more considering bounded measurable functions. We are no more imposing the condition that the set E has finite measure. Okay? But we are imposing a condition, the two other conditions, namely that the functions are non-negative. So remark we take not anymore consider the function to be bounded not bounded. Also do not assume E, the domain of the function, is bounded. Is of finite. E is of finite. So that's the two relaxations. To the analysis, we assume two things. One, the function is non-negative. Now, we did not make this assumption in our earlier part. Second condition is that the function has a support of means the function is significant only on a set of finite. That is the assumption that we. So we are not relaxing altogether, but to facilitate our analysis, we are for the time being taking up only the non-negative functions, and also we assume the function is significant only on a set of finite measure. Therefore, partly our assumption is considered or is taken care of. That's very interesting. So how do we work on this? But we have not explained to you what exactly, right? So I have qualitatively explained this here, what we mean by having a finite support. So let me do that first and give a formal definition of this, what we mean by a support. A measurable function on a measurable set E is said to vanish outside a set of finite measure if there exists a measurable E with measure of E naught finite such that F is identically equal to 0 on complement of E naught in then we say F has support of finite. So essentially what we understand by the word support is that it's a subset on which the function is non-zero. Okay, so it's a subset on which the function is non-zero. Okay, because as far as integration is concerned, the set of points, there is no contribution to the integral from the set of points where the function is 0, because the way in which we have defined the function, see, we can always extract out this E naught and write E as the E naught union E naught. And suppose the function is 0 on this, then as far as integration is concerned, f is the values f takes only on E naught alone contributes to the integral. Now that is the problem. Okay. So you have this one, suppose f, this is what you have. Therefore, what happens if f is 0 here, then you see that this portion will contribute only a 0 to the integral. Therefore, essentially, integral over E that is the reason why we talk about support of finite measure. Now you see, we are now working on functions, measurable functions on E naught. E naught is a set of finite measure, and we also assume for the time being that f is non-negative. So these are the two assumptions. So let me just put this across for clarity. Many occasions you would need to use this word support. And this is our E naught. So even when measure of E is infinite, for example, the whole of R, if f is bounded and measurable and measurable. On E, finite support E naught and we can define integral over E I have worked out the logic for, because the E slash E naught portion will not make any contribution to the integral because the function is 0 on that. Okay. So we shall now consider. So in this stage we will consider at this stage only non-negative push the theory through non-negative measurable function only with the support of so we take a measurable function only the support of finite. Here we are not going to assume f is bounded. Okay? We are not going to assume f is bounded. F may take even infinite values. That is possible. I will make some remark about this later because the sort of what you call calculus we introduced on what are called the extended real valued functions would be required to work in this scenario. Okay, let me do that. So what I do is I have to define integral definition. Let f be a non-negative measurable function. Now we define the integral of f what one does is we approximate. See, you recall the for bounded measurable functions defined on sets of finite measure we have considered. There we approximated the function from above and from below by what are called simple functions. That is the strategy that we have. So here let us see what we do. Okay. So we know for such functions everything is the The strategy is already explored. We have defined the integral. Okay. Now what we are going to do is these class of functions where we are not possibly assuming f is bounded, so that assumption is not there, but we are taking it to be non-negative. We do the following. We'll approximate it from below, okay, by what you call bounded measurable functions of finite support and with the appropriate inequality. So let me write this. We define by integral of for E of f is defined as supremum h where h is bounded, h is measurable, it's of finite support, with 0 on. Okay. So we reduce this problem to working with the one that we have already explored. What was that? We had E to be assumed to be of finite measure. Okay. When we had F measurable, F bounded. Okay. So this was the assumption that we have made. Therefore, what we are going to do is now take all bounded functions h which are measurable and of finite support, satisfying the inequality 0 less than or equal to h less than or equal to f. Okay. Now I'll give one. See, sometimes what happens is through the limiting process you may now get the integral to be infinite also. That's also possible because we are now no more assuming the function to be bounded. So that is also now under our integration possibility. Okay. For example, take this function. Look at this example. You look at this function, the function f of x 1 on belonging to so the function is, of course we are considering this function on x belonging to 0. Now f is greater than or equal to 0. F is measurable. F is measurable. And you see that E is of finite. Because E is in this case equal to 0. Now you see that you can take an H. You can take an H with the following properties. Take H to be equal to, or let me write H and X. Equal to 1 for X belonging to and equal to N now you see that you have 0 less than or equal to H, N less than or equal to, this condition is satisfied. Now what about the integral of Hn? Integral of Hn is essentially equal to 1. For every n over 0. Okay. But what about Hn? Hn is something that below this function. At rational points, Hn takes the value. I mean, they are equal. At irrational points, you see, sorry, at irrational points, they are equal. At rational points, what happens is Hn takes the value n, which is less than infinity anyway. But it's not a bounded function. I mean, sorry, this sequence of functions, the given function is not a bounded function. Okay. So, how do we fix the integral of this to see that this is equal to 1? Now, take the limit of all this, or you take the supremum over all this. Okay. So, you can find lot of functions with this property and then you can apply this result. You can even do this. So, a second example is the same example. F is from R to R. R is an extended variation. F is equal to one on X belonging to Q complement. This is equal to 0. Sorry. This is equal to infinity. Q. And further, this is equal to 0. Now you can work out the integral of this. So this is no more. So the domain of is measurable, but not of now you can take H as to be equal to 1 or even less than that, say to complement, and then take any value n and this is equal to 0. Infinity. Then you have this condition. Now you see that the integral of h over this is equal to 1 for any h, every h of this kind. Okay, so at most it is equal to 1. Therefore, you see that you can apply the supremum condition and gets is nothing greater than that. Okay, so you can analyze this in depth, or you can construct such examples and then analyze. So let us retain this definition here. Now for such functions, we will work out the integral. So we have now defined. See, the point that I wanted to make is that there are situations where this would come infinite. So here, okay. For example, you take this one. Take e to be 0, 1. and this is equal to say 0 at x. So measurable set. I mean, you need not take this part at all. You can consider the interval open, closed interval 0. Now what happens? You take, see, if you look at the graph of this function, see here 1 by x is this, it takes the value 1 here, and then here it takes the value this. This is the graph of the function. This is the graph of the function. This is asymptotic. This is. Now what you do is you take h as any function, h to be equal to takes the value 0. Sum m take an hx like this. Now this hx is something which takes a value 0 here, takes the value n here, then r. So this is below fx. So you see that this is satisfied. And you see that h is measurable. H is bounded. Okay. So h is bounded, measurable, and on a set of finite measure. Therefore we can, so integral but one can show that the supremum of bounded, finite support such that 0 is equal to, now this you can show. Okay. So even for that, you see it is well defined. Okay. Remember, there is no ambiguity at all because we are assuming the function to be non-negative. So it could be either finite or plus infinity, which being obtained as the supremum of this part. So that is the definition. Okay. Then once you define this, you can prove the following. So we can prove the following theorem. Let F be a non-negative measurable function where measurable function only, then if integral is equal to 0, if and only almost everywhere on. What we mean by almost everywhere? We say that a property is satisfied almost everywhere it is valid everywhere except on a set of measures. For example, suppose on the interval 0, 1, at all irrational points a function is equal to 1. So at all rational points it may take any other value. In that case, what you can say is that the function is equal to 1 almost everywhere, because the set of functions where it fails to hold is of measure 0. Okay, so that's the meaning of almost everywhere, which you would have already seen this. Now, let us come back to the statement of the theorem. The function is a non-negative measurable function only. Then integral of f equal to 0 if and only if f is identical to 0 almost everywhere. So from this integral, this is important. It's non-negative. Okay. The function f is non-negative is important. Any non-negative function has its integral equal to 0 means the function itself vanishes almost everywhere on its domain. That's the significance of this theorem. You can look into the proof of this theorem. Okay. Now, further properties of this integral are, so we have already defined what the integral is for such functions. The linearity and monotonicity can be extended. What do we mean by that? Okay. So let me write. So let non-negative measurable functions only then for positive we have the following property. This needs some work to prove this. Now we are assuming f alpha positive and beta positive to assure that alpha f plus beta g is of the same class, so that this integral is well defined. Okay. So this is the linearity for this. Now the further we can show that f is less than or equal to g on E this implies that you can write this property all can be tagged with say this can be this condition can be stated with f less than or equal to g almost everywhere. Okay. So I think this is a place where probably I would like to. Okay, one more property I want to state. This is the additivity over so that we are just on the brink of taking up the convergence. Over domains of this is the statement of the theorem. F non-negative measurable disjoint measurable subsets of E, then that's it. Okay. So here you can slightly improve it and say that almost every. So I think this is a place where I would like to stop. Okay. Thank you very much. We'll come back to the convergence theorems. Okay. So thank you very much.